first one has to do with the production of ammonia. We have been told that the enthalpy of formation is minus 46.6 kilojoules per mole. This is making 2 moles worth. So the delta H for this reaction is minus 92.2 kilojoules. We're asked about 2 temperatures. They're giving us K1 and they're asking us what K2 is. Once we look at all these things that they have given us, we realize that we want to use the Van 't Hoff equation for this. So this is a quantitative version of the qualitative thing that we were talking about earlier, which was that since this is exothermic, if I change the heat and I raise the heat, I'm expecting it to favor the reactants. So I am going to expect K2 to be a smaller number than K1, and I'm going to calculate it now. So let's just write down what we have for our Van 't Hoff equation, and we can just start putting in some numbers in here. However, we are going to keep track of the fact that we're trying to find K2 and we already know K1. This is going to be minus 92,200 because I'm going to get rid of that kilo and turn it into joules so that they will cancel with the 8.314, which is in joules. And then I have 1 over 298 minus 1 over 400. Now here's something I want to show you on the calculator. This looks terrifying. If you have this button though, it is a lot less terrifying. You put in the 298 and you put that in. Then you say I'm going to subtract and you put the 400 in and you hit the button again. That's going to be the whole parenthetical expression. So I have just figured out what this number is. And I can just go ahead and multiply it by 92,200 and divide it by 8.314. And I am going to get a negative 9 point, who knows how many of these I should keep. But this then is equal to natural log of K2 over K1. Trying to find out K2 and it's stuck inside this logarithm. Remember, a logarithm is an exponent. So if this is a logarithm, then it is an exponent. I can just figure out what e raised to this power is. So I want to do that. Second, e to the x, hit that, and I get, ooh, that's not a very big number. And it's really expressed in a very strange way. Let me write it a slightly different way. Times 10 to the negative 5th. Doing this just makes these guys cancel each other. K2 is 7.56 times 10 to the negative 5th times K1. K1 is 780. So I'll just multiply this by 780. And I get, ooh, I should probably round this back to 2 sig figs because there's not even a decimal point on that K1. 059. That is a big difference. So this higher temperature ended up giving me a much lower K value. At the higher temperature, it's way over to this side. And you can see that from the graph that we were talking about before. We're taking nitrogen and oxygen and making dinitrogen monoxide. This has a positive delta G. Okay, this is going to be different than the other problem. I didn't mention delta G before. But I do have delta H, and I have T1 and T2. And it says, what are the values of K sub P at these temperatures? And I'm going to have to work up K sub P the other way. First thing I need to do is say this delta G, this is per mole, and I'm making 2 moles of this. So delta G for the reaction that I've written has to be twice that number. So it's going to be 208.4 kilojoules for the reaction as written. And then I'm trying to find out what K sub P is at 298. I can just go ahead and say that that is E to the minus delta G over RT. Let me just put in those numbers now. So that will be E to the negative. Okay, now remember, R is just in joules. This kilojoules has got to go. And then over RT, the 8.314, and then the temperature's 298. And you can see that all the units will end up canceling because that's the Kelvin, this is per Kelvin, that's gone, joules, joules, they're gone. I'm going to get E to the minus 84.11, 2.95 times 10 to the negative 37 for K, which means essentially none of this is made normally at 298 Kelvin. It all stays like this. Well, that's a good thing because we breathe this. We don't want to breathe that. That's very bad. Okay, what about the other temperature? Well, it's a higher temperature. This I can see the delta G. They told me the delta H also. Delta H says that it's going to be endothermic. So if I raise the temperature, I'll make more of this. So I should end up with a K value that is bigger at a higher temperature. Now that I know the first one, I can go ahead and use the Van Hoff equation to do the second one. And I'll start putting in the numbers. The delta H is again per mole, so I'll have to double it. So instead of the 82, it'll be 164.2. There, it's in joules now. And the R, 8.314. And then here the 1/298 was the first temperature, and 2000 was the second temperature. I will do the same process as I did up here, but you'll notice this is a positive number where the other one was a negative number. 56.4. This is still trapped E. These will cancel and you'll end up with K2 compares to K1, and this will be 3.12 times 10 to the 24th, which sounds crazy big until you realize that K1 was so small. So K2 ends up being the 3.12 times 10 to the 24th, but that's being multiplied by our friend here, which was very small, times 10 to the negative 37. And when you get all done, K2 is still small at 9.2 times 10 to the negative 13. So even at 2000 degrees, we don't make a lot of dinitrogen monoxide.